Hello, everyone, and welcome to Virtual Planetarium Exploring Space. My name is Emily. My pronouns are she and her, and I will be your moderator during this program. So that means that I'm the one actually watching the Q&A box if you are watching here on Zoom. Now, that Q&A box is important because since we're all in this webinar format program, you will not be able to talk to any of our educators except by typing any of your comments or questions into that Q&A box. So if you do have questions or comments, throw them in that chat box and I will relay those messages to our educators today. Now, I also want to talk about captions with you all. We do have automatically generated captions that are going right now. You probably even see them at the bottom of your screen. Those will be on automatically during the program, but if you find them distracting, you are welcome to turn them off by clicking on a CC button on your screen and then select Hide Subtitles. So with that, I think that's everything that I needed to share with you. I'm going to welcome our educators to come on screen and we'll get started.
Thanks, Emily. Hi, everybody. My name is Katie. My pronouns are she and her, and today I will be your educator or your guide as we explore some black holes, but I can't do it alone.
Hello, everybody. My name is Saya. I also use she, her pronouns, and I'm going to be handling the visuals today.
Awesome. So yes, today's topic is going to be all about black holes. They are one of my favorite objects in the universe. They're so fun and mysterious and kind of spooky, but in actuality, not so spooky. And they're just super fun. We are also going to be talking about active galactic nuclei, which are basically galaxies that have black holes in the middle that are eating up material, kind of like what you are seeing in this animation here. So in general, black holes get a fairly bad reputation, right? We kind of tend to think of them as these giant space vacuums, but they don't actually suck things up. Objects can fall into black holes if they get too close, but you can actually safely orbit a black hole if you're far enough away. So for example, if we were to take our sun out of the solar system and replace it with a black hole that had the same mass, the Earth would continue to orbit the way it is right now, and we wouldn't have any problems except we'd get really cold. That would be a big problem, actually. But the actual orbit of the Earth wouldn't change at all. So what exactly are black holes and are there different kinds? We're all going to get into that right now. So this graphic here shows you the objects that can be left over after stars die. So that's kind of over on the left part of the screen. And then we have different size of black holes. So white dwarfs are objects that are left over after an average star dies. So something like our sun in 5 billion years eventually will turn into a white dwarf. And we have neutron stars, so very massive stars can turn into those. And then the most massive stars in the universe, when they die, they leave behind black holes. And there are 3 different kinds. There are stellar mass black holes. Those are the ones that are directly left over after a star dies. Then there are intermediate black holes, which are still very, I guess, less understood than other black holes. We haven't really found any yet, so we'll talk about that later. And then we have our supermassive black holes, which do not form from stellar collapse, but can form from other processes. So we're going to talk about that as well. All right, so let's dive into stellar mass black holes first. So these black holes have the same mass as maybe a few times our sun to about 100 times our sun. And mass is a measurement of how much stuff something is made of. So you know, you and I have mass. Our mass doesn't change no matter where you are in the universe. You are always made of the same amount of stuff. So for stars, and when they die, they are made of the same stuff. They just kind of take up different amounts of space. So when a very massive star starts to near the end of its life, it will run out of fuel. and explode outward in a massive event called a supernova. So in this animation here, we can see this really massive blue star that is running out of fuel. It does an initial kind of collapse, and then it bounces off its core and expels material out into space. And this material is traveling at a significant fraction of the speed of light. But the core of the star, so most of its material there, continues to collapse in on itself, and it gets so dense that it actually collapses into an infinitely small point. So you have all of that mass from that star collapsing into this small point, which means that it has a measurable mass, but it has an infinite density. And it also has an extremely strong gravitational pull. So this is a diagram of a black hole to we can talk about the different parts of it. So right at the center of this shadow here that you're looking at is the singularity. That is that point where density is infinite, where all of that mass has just squished into a single teeny tiny point that is infinitely small. That would be classified as the singularity. The edge of that shadow there is called the event horizon. So that's kind of like the point of no return. More specifically, that is the point around a black hole where you would need to be traveling faster than the speed of light to escape it. So anything that crosses the event horizon will never, ever be able to get back out, including light. There are some other terms here that we can see, like photon sphere and innermost stable orbit. These are terms for material and light that's orbiting around the black hole, but maybe hasn't actually gone into it. Those are just some stable orbit areas. Then we also have the accretion disk. So if objects or matter, gas, dust is falling into a black hole, it heats up and it forms this hot ring around the black hole. So that's called the accretion disk, which we'll be talking a lot about. And then depending on how heated this material is and how much of it, some black holes can release electromagnetic radiation in the form of jets, but those have to be very, very massive. So probably wouldn't see jets in the lower mass or stellar mass black holes. All right, so that's a little bit about the origins of black holes. Again, that's stellar mass, but let's move on to our supermassive black holes now. So stellar mass black holes have anywhere from 100 to, or a few times the mass of our sun to about 100. Supermassive black holes are usually millions to billions of times the mass of the sun, and they can form from a couple of different ways. So one way is something that you're seeing right now. This is an artist's interpretation of a black hole that's accreting material. So in this particular instance, we have a black hole and a very massive star that are orbiting around each other. And the black hole, because it's so gravitationally strong, is actually, and the star is close enough to it, it's accreting that material. So that material is being pulled away from the star, and it looks like the black hole is eating it up. That material makes the black hole gain mass. And so over time, you can get a black hole that's much more massive from these types of events. Another way that supermassive black holes can form is by merging. So if you have two black holes that are in orbit around each other, eventually they will collide and form an even more massive black hole. And this is a common theory as to how these supermassive black holes at the centers of almost every galaxy form. And the Milky Way and Andromeda are actually going to collide in about 4 billion years. And so there are supermassive black holes that are at the center will collide as well. All right, so speaking of supermassive black holes at the center of galaxies, I do want to talk about our own supermassive black hole, because our galaxy, the Milky Way, does have one. It is called Sagittarius A star, and it is right in the center. Now, from this artist's image of our galaxy, because we've never seen it from the outside before, that would take way too long to get something out there. We're talking millions of years. So we have a good model. But right at the center there, it looks like this big kind of bulge of light. There are lots and lots of stars, tens of millions of stars in this part of the galaxy. But right in the center is a supermassive black hole that all of these stars are orbiting around. Our supermassive black hole has the mass of about 4 million times the mass of our sun, and it's holding a lot of the galaxy together. It's not the only thing that's holding the galaxy together, but it is responsible for a lot of it. And we think without this black hole, our galaxy may never have formed in the first place. So if we can't really detect black holes because light can't escape them, and we have a hard time seeing our galaxy, how do we know that it's there? Well, we can use high-powered telescopes to peer into the central part of our galaxy, and we can observe the motion of stars in this area. So in this video that you're seeing right now, all of the little sources of light, those are stars. The colors indicate motion and temperature. And then right at the center there, you'll notice that some of those stars move very quickly, and they actually make little orbits. And so there's one star in particular actually called S2 that astronomers have been following because it is the closest star to the supermassive black hole at the center of our galaxy. And by tracking its orbit, astronomers can actually tell, and mathematicians as well, can tell how massive whatever object is sitting at the end of that star's orbit. So the only thing that would be plausible, that is invisible, that would cause the star to move in such a way would be a supermassive black hole. And of course, we can't actually see it. And we haven't been able to see black holes for a very long time until very recently when we got the first ever picture of a black hole. So this picture is not of Sagittarius A star. It's not our own black hole. It's a black hole that's at the center of a galaxy that's 55 million light years away. The galaxy is called M87, and this black hole is even more massive than the Milky Ways. This black hole has the mass of 6.5 billion times the mass of our sun. And so it took a lot of power in order to resolve this image, but basically this is an image of material around the black hole in radio waves. So it's not what you would see with your eyes, but it's if you were to look in the radio part of the electromagnetic spectrum. And the shadow there in the middle does represent part of the black hole. The edge of it is not technically the event horizon. It's a little bit more than that. But then we can see all of that heated material around it. So this black hole is accreting material. And the brighter section there, because material that's around a black hole is moving at a significant fraction of the speed of light, which means that there's all kinds of weird physics going on. Think special relativity, and like time slows down depending on if you're observing from the outside. There's a lot of weird stuff going on there. And there is an effect called relativistic beaming. So basically any material that is moving toward you as an observer is going to look a lot brighter than material that's moving away from you. So that's why we see one very bright side compared to the rest, is that material is moving toward us from our perspective, if that makes sense. All right, so how did we take this picture? This is super cool. It took a lot of telescopes networked together around the Earth to actually get an image of this black hole, because again, this galaxy is 55 million light years away. So it takes light 55 million years to travel to actually reach us here and our telescopes. So to resolve something that far away, and also that black hole, like size-wise or volume-wise, is pretty small. So to take a picture of something like that, you would need an Earth-sized telescope in order to resolve an image like that. And so we can't create an Earth-sized telescope, unfortunately, but we can simulate one by connecting all of these telescopes together and then kind of piecing images together, kind of like a puzzle, in order to get this picture of the M87 black hole. This is called the Event Horizon Telescope. And again, it's just an array or a bunch of them connected together. All right, before we move on, I want to check in and see if there are any questions.
Yeah, Katie, we have so many great questions, and I want to start with one from Shane in 5th grade. They asked if there's anything that can actually go faster than the speed of light that could possibly escape a black hole.
That's a good question. So nothing that we know of in the universe can travel faster than the speed of light. So if light can't escape something, then there's not a whole lot of luck for the rest of us. There is one thing, I guess, technically, it's not really a thing, but there is one phenomenon that is faster than the speed of light, and that's the whole expansion of the universe. But that's okay because it's actually space that's moving outward rather than an actual object. So that's the only thing that goes faster than the speed of light, but it would never get sucked into a black hole or anything like that.
Cool, thank you. Someone else is wondering, you mentioned that our sun will turn into a white dwarf in 5 billion years. And they're wondering, if the sun goes away, will a new star ever appear in its place?
That's a great question. So when an average star dies, we have the leftover core, which is the white dwarf. There's a lot of material that gets kind of pushed out into space. And that material might eventually go on to form new stars. It's pretty unlikely that we would have a new star right where the sun would be. But eventually that material will probably go on to be part of new stars.
Cool. And how about one more for now? Can you just tell us how exactly a black hole can hold an entire galaxy together?
Yeah, so it doesn't hold the entire galaxy. It holds a good chunk of it, like all of those kind of central stars in the middle there. Everything is orbiting around this black hole. But black holes, even supermassive ones, don't have enough gravity to keep literally everything in the galaxy together, like the outer edges. So that is actually from something called dark matter and the gravitational effects from this dark matter that is holding the entire galaxy together. So the black hole is keeping a bunch of the central region, but really it's dark matter that's responsible for keeping the entire thing together. But that's a whole separate topic that we'll go into in another show.
All right, thank you. We'll definitely have a couple more at the end if we have time for it.
Great. Yeah, so let's move on to those mysterious intermediate black holes. So these astronomers have been looking for years because they're hard to find. We weren't really sure if they existed at all. And that's because anything in between here, in between these two other categories, there's no star that could be massive enough to collapse into a black hole of this mass, of this kind of middle chunk, missing chunk here. And then with supermassive black holes, they tend to be in very high energy, high density environments. So areas where there are lots of stars clustered together, maybe some collisions going on, lots of gas and dust. And intermediate mass black holes would lack that environment. They would get bigger, I guess, if they were in that type of environment. So they've been missing for a while, but there are some candidates out there. Astronomers think they are starting to find them, which is exciting. And their formation is, of course, the next question. So there are lots of different hypotheses about this. It could come from smaller black holes colliding, kind of like what we talked about with supermassive black holes, although that takes a lot of stellar mass black holes to create a supermassive black hole. But that could be the same case for these intermediate ones. They could come from collisions of stars in clusters, potentially. They could also be left over from the Big Bang as well. So there's a whole bunch of different ideas, but astronomers think they finally found these weird intermediate mass black holes. All right, so the next thing I want to talk about is when a supermassive black hole at the center of a galaxy is accreting material, meaning that there is a massive cloud of gas and dust or stars that are falling into the center of a galaxy, into its black hole. So this is another artist's rendition of the central black hole in the galaxy M87, the one where we took the picture of the black hole, of it actually accreting material. So this material is moving very fast, so fast that it heats up. It's experiencing a lot of friction between the other gases around it, and it's experiencing extreme gravitational forces. And so it lights up and it heats up. And there's so much energy involved in this process that the black hole will actually not really spit out, because there's nothing coming from the black hole itself, but it will kind of redirect some of this material into jets that look like they come from inside the black hole, but they're actually not coming from the black hole itself. It's coming from the accretion disk around it. And so those jets that you're seeing here are extremely powerful, high energy electromagnetic radiation or light. And they are almost always like these beams here. So we can go into different types of active galactic nuclei. So basically, if the black hole's eating up material, it's an active galactic nucleus. And then there are different types of those AGN, we can say for short. So this is a real picture of the same galaxy, M87, the one with the black hole picture. And this is a picture of its jet. So what tends to happen with active galactic nuclei, or we can say quasars in this case, because this is a quasar, is that the jets and the luminous central region are so bright that you can't really see the rest of the galaxy when you're making observations through a telescope. So what we tend to see are these really incredibly long, like we're talking thousands of light years, jets of electromagnetic radiation spewing out from the black hole at the center of the galaxies. All right, so as I mentioned, quasars are just a type of active galactic nucleus. There are so many different kinds, and it really just depends on the angle that you're looking at something. So a quasar specifically, they are the most powerful, but they have to be viewed from the side. So if you're looking through a telescope and you see a galaxy from the side with two jets kind of coming out of either side, that's a quasar. And so you're looking at one right here. This is an X-ray image. That's why it looks very strange. But these jets tend to emit the highest energy form of radiation, which is X-rays and gamma rays. The next type of AGN is a blazar, which is a quasar just seen from a different angle. Blazars are when the jets are directed right at you, at the observer. So it looks like just a point of light. But these, if you remember, we talked a little bit about relativistic beaming around black holes. That's experienced with blazars. They appear a lot brighter than they actually are because that light is coming toward you. It's directed right toward you. And then the last kind, before we stop for questions, is called Seyfert galaxies. So these types of galaxies have active galactic nuclei, but they're not as powerful. They're not emitting quite as much energy or radiation. So the whole galaxy is visible. And it actually takes closer inspection by looking through telescopes and using spectroscopy to examine the wavelengths of light at the center in order to determine whether or not that black hole is accreting material. So these are tougher to find, but they are also a type of AGN. All right, let's go ahead and leave the rest for questions.
Sure, thank you, Katie. So I have a couple related questions. People are wondering, how long does it take for a star to explode and then become a black hole? And similarly, how long would it take for two black holes to merge into one?
Yeah, so it's very quick. The amount of time that a star takes to explode is it's like a fraction of a second. And then there's the shock wave that kind of permeates through the star. And again, that takes a very short amount of time. The actual collapse is also very quick. I don't actually know how long that process takes, though. I imagine it's like less than a second. I don't know if Talia, do you have that on the top of your mind?
Again, I know it is very quick in terms of like how many seconds it is. I'm not sure, but it is very, very fast. A lot faster than you would think for something as large as a star collapsing.
The same is true for collisions. The actual kind of moment of collision is very quick, but this whole process of starting to collide so that you have two objects that are orbiting around each other, that process can go on for a very long time until finally they have the collision point, which would take a few seconds.
Awesome, thank you. Could you tell us approximately how big is a supermassive black hole?
Yeah, a supermassive black hole can be anywhere from like 100,000 times the mass of the sun to billions of times the mass of the sun. So it's a huge range. Our supermassive black hole, about 4 million times the mass of the sun. The one in M87 is about 6.5 billion times the mass of the sun.
So amazing. And let's do, how about one more? This is from a grade 3 class that asked the question earlier about the sun. They're just wondering what would happen to Earth if the sun went away. Maybe you can give one example of the terrible things that would happen.
Yeah, so if the sun just disappeared, it would take 8 minutes for the Earth to feel it because the sun is 8 light minutes away. And we would get very cold. We'd also kind of leave the solar system behind because the Earth wouldn't be stuck in orbit around the sun anymore. So it would just kind of float off into space. We'd get very cold.
All right. Well, thank you so much, Katie. I think we are basically out of time. So Katie and Talia, do you folks want to say goodbye to everyone before we wrap it up?
Bye, everyone.
And everyone, thank you so much for all of your participation in that Q&A box and all of your questions. They were amazing. And I'm sorry that we don't have time to talk about all of them. If you enjoyed today's presentation, I do recommend visiting our website at mos.org/mos@home to check out more of our virtual offerings. You can also go to Facebook or YouTube to see any of our previously recorded content. And we also would just love it if you could support the museum by visiting engage.mos.org/welcome. So with that, we will see you next Tuesday for another virtual planetarium. And I hope you all have a great day. Bye.